Section 5.1, Areas and Distances. Now we are about to start to see the second most important part of this class, what is called integration, and that becomes a big part in calculus 2. So to start this, there are many motivations for the development of this whole class, calculus. One of them was the problem of calculating areas for complicated shapes. For example, to calculate the area of a circle, the ancient Greeks circumscribed polygons, meaning they drew circles around polygons, and started to increase the number of sides. So for example, in this picture here, we've got a 4-sided polygon, a square, inside of a circle, and then an 8-sided polygon and a 12-sided polygon. The idea is with increasing the number of sides, the polygon starts to look closer and closer to a circle. Those polygons, finding the areas of those is actually something that's not too hard to do. So they could calculate the areas of the polygons. And as the number of sides increased, they would notice that the areas started to approach pi r squared, which we now know is the area of a circle. So notice the word that we used, closer and closer, and then approach. This is the idea that we've seen with limits. If we wanted to find the area under the curve, for example, y equal f of x, bounded in the region from a to b, then we don't really have a place to start. That is a complicated area that we don't really have something that we can do for it. But if we take the idea of circumscribed polygons, maybe we can use some shapes that we do know the areas of, like rectangles, and see how many we can put inside of the region that we're trying to find, and then maybe we could approximate the area. Then if we increase the number of rectangles, we might get closer and closer to the actual area. This is also related to how we started the whole class, when we were trying to find the slope of a tangent line. We started with something that we knew, like a secant line, and then we took the limit, in that case, of the secant line slope to see that it approached the slope of the tangent line. So we're going to start with things that we know how to approximate, that we know how to find, rectangles, and use them to approximate areas, and then take the limit of those approximations as we start to increase the number of rectangles. So to get us started, let's look at this example. Approximate the area under the parabola y equal x squared from 0 to 1 using rectangles. So first thing I'm going to do is just draw a picture. So let's start by drawing a picture. And this is just going to be a parabola, and I only need to focus on the region between 0 and 1 on the x-axis. So 0, 0 is on the graph of the parabola. So is 1, 1. And then my curve would look something like that. And then I'm going to split up my region into 4 pieces. So from 0 to 1, I'm going to cut it in half, and then I'll cut those halves in half. If I take those numbers that are on the x-axis now and plug them in, I would get function values on the curve. And we're going to call those 1/4, 1/2, 3/4, and 1. We're going to call those right endpoints because they are the right-hand number of the intervals 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and this one should say 3/4 to 1. And from those right endpoints, I'm going to create rectangles. The way that I can create rectangles is just use the right endpoints as the heights of the rectangles. So you can see that I have these rectangles that are each going above the curve, but since they're rectangles, we can find the area. So the area of a rectangle, that would just be, you could say, width times height. So I could find the area of this first rectangle. The width is, how wide is it from 0 to 1/4? That's just 1/4. The height, that would be the function value at 1/4. Because as we saw, the heights are measured from where is the point on the function, that becomes the height of the rectangle. So this just means f of 1/4, which our function is x squared, so it means we're just squaring 1/4. So I'm just going to write the width 1/4 times 1/4 squared. And then we could do that for the other rectangles. So for the next rectangle, the area would be, again, the width, and then it would be times the right endpoint, 1/2 squared. And then we could do that for the next two. So for the third rectangle, just by counting from left to right, that area would be 1/4 times the right endpoint, 3/4 squared. And then the fourth rectangle, that area would be 1/4 again times the right endpoint, 1 squared. So then the total area would be the sum of these. One-fourth times 1/4 squared plus 1/4 times 1/2 squared plus 1/4 times 3/4 squared plus 1/4 times 1 squared. So I've summarized this just below. With these rectangles, the sum of the areas are, as we see here, I could factor out the 1/4 that's in common with each of these products. And then I can add what remains, the squares of 1/4, 1/2, 3/4, and 1. And then when I multiply everything together, I would get this approximation, 0.46875. But obviously the area we want should be smaller than that, because these rectangles were going above the curve. This is an over approximation. So now let's use smaller rectangles, ones that would under approximate the area. In this particular case, that would use the left end points of the intervals. So that means for my intervals, I'd be using 0 and 1/4 and 1/2 and 3/4. So this would give me heights of f of 0, f of 1/4, f of 1/2, and f of 3/4. So by the same logic, the sum of the areas would again be the width, 1/4, that's in common with all of those intervals, times the sum of squares. In this case, 0 squared, the left end point that comes first squared, plus 1/4 squared, plus 1/2 squared, plus 3/4 squared. And that would give me an under approximation of 0.21875. What that would look like as a picture, if I'm using left endpoints, then I'm using 0, 1/4, 1/2, and 3/4. The fourth rectangle would look like that, because it's using the left endpoint 3/4 to determine the height. And then the other ones you could see would all be below. And in fact, the first rectangle, by using the left endpoint of 0, it wouldn't even have any height, because f of 0 is just 0. So that's why we get an under approximation of 0.21875. So now we have a little bit of a range, and we know that our actual area should be somewhere in between there. So then the idea is we only used 4 rectangles. What if we use more rectangles? So we're going to see that then in the next example. Show that the sum of the areas using rectangles from right endpoints in the previous example approaches 1/3 as the number of rectangles increases. So first of all, again repeating here, we can write the sum for the first area that we found above as 1/4 times 1/4 squared plus, and now I'm changing things up a little bit. Instead of writing 1/2 squared, why don't I write that as 2/4 squared? Because 1/2 is certainly the same thing as 2/4. And then 3/4 squared, we have that again. And instead of 1 squared, I'm going to write that as 4 over 4 squared. So then I have some consistency with my fractions. So that came from 4 rectangles. So then following the same sort of logic, if I had n rectangles, which means any variable amount of rectangles, 6, 8, 10, 12, doesn't matter, but let's call it n, the sum would then be, instead of 1 over 4 for 4 rectangles, 1 over n, and then times the sum of squares, 1 over n quantity squared plus 2 over n quantity squared plus 3 over n quantity squared plus going all the way up to n over n quantity squared. I can factor out more common factors like a 1 over n squared. That gives me 1 over n times 1 over n squared is 1 over n cubed. And then what's left inside would just be the sum of those numerators squared. So 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. Now this quantity right here, that's called the sum of square integers. And by number theory, that is equal to n times n plus 1 times 2n plus 1. So we're just going to take that as a given, which means that the sum is now this. So now let's do something that we can do in this class. Let's find the limit of that as n approaches infinity. So let's find the limit as n approaches infinity of 1 over n cubed times n plus 1 times 2n plus 1 divided by 6. So just to simplify some things here, I'm going to multiply numerators and denominators. So first, I would have 1 cubed times n plus 1. I'm going to write that as n squared plus n. And then times 2n plus 1. I still have yet to do that. And then divided by n cubed times 6. That's 6n cubed. And this becomes the limit as n approaches infinity. And I would get 2n cubed plus 3n squared plus n divided by 6n cubed. And since we've learned about L'Hopital's rule, we know that we could evaluate this and just take derivatives, but we can also think that this relates to a horizontal asymptote of a rational function where the degrees are equal in the numerator and the denominator. And we even learned in pre-calculus that the limit of this as n approaches infinity is just the quotient of leading coefficients. So this turns into 2 over 6, and that's 1/3. So now this one example is just laying the foundation of what you're going to be doing in this section and in the following sections. So now let's generalize some results. Instead of having a specific function like f of x equal x squared, let's just have any general function f of x bounded by x equal a and x equal b. And we're going to divide that region into n rectangles. The width of the whole interval would just be the difference of the endpoint b minus the endpoint a. And then the width of each region would be that total distance divided by n. This works for our example up above. Here, if we thought of 1 minus 0, that's b minus a, divided by n, which was 4, that gives us a width of 1/4. So we're just generalizing that below. We're going to call that delta x. So the change in x is b minus a divided by n. We then divide the whole interval from a to b into sub-intervals. And there would be n of them, just like we had up above. We had 4. So the first sub-interval would go from x0 to x1. The next interval would go from x1 to x2. And then that would just continue, same pattern. And the last one would be xn minus 1, comma xn. So here x0 is the same thing as a, the beginning of the region, and xn is the same thing as b, the end of the region. The right endpoints, just like we saw before, we could just use a and delta x to get each one of those. So again, if you want to think of how we got the right endpoints in our original example, x1 would have been 0, the beginning, plus delta x, which we said was 1/4, and that's 1/4. x2 would have been, again, 0 plus 2 times 1/4. That's just 0 plus a half. That's a half. So our example is still just following from this generalization. So now generalizing some more, the ith rectangle, I is just somewhere between 0 and n. So I is some rectangle in between, but we just want a general rectangle. So the ith rectangle has width delta x. All of the rectangles have the same width, and the height comes from the function. So f of xi. Then the area of the ith rectangle is delta x times f of x sub I. And then the sum of the whole region we will call r sub n, and that's equal to delta x times f of x1 plus delta x times f of x2, etc., all the way to delta x times f of xn. This is just like our first example. It's using right endpoints, and that's why the letter r is here. So then the area of the region that lies under the graph of f of x between x equal a and x equal b is capital A, and that is equal to the limit as n equals infinity of this sum that we just wrote down, r sub n, which you could also just think of as the limit as n approaches infinity of that same summation that we have there. A similar definition can be made if we used left endpoints. The only difference is the indices start with 0 and end with n minus 1. So instead of x1, x2, x3, it would start x0, x1, x2, etc. We could in fact also use any point in each of the rectangles, which has an x-coordinate x sub I star, which just stands for any sample point from each rectangle. So the point is, it doesn't matter if we use right endpoints or left endpoints or any other point in the interval, we're still going to get the same idea for the area. And so then the area that we're going to have will be the limit as n approaches infinity, again, of a sum. And this summation is the idea of adding up all of your n rectangles. So you start with I equal 1, the first rectangle, all the way up to n, the last rectangle. And you'd have your height, f of x sub I star, and then your width, delta x. So we're going to dive in more to that limit notation in the next section. So to finish up this concept of areas, let's take a look at another example to solidify these concepts. So in this example, let f of x equal 1 plus x squared, so sort of similar to our first one. And we're going to estimate the area under the graph of f of x from x equal -1 to 2 using 3 rectangles, but in part A, we're going to repeat using right endpoints, and in part B, we're going to do something different. We're going to look at midpoints. So let's start again with a picture that we can use for the whole problem. This is a parabola that's just been moved 1 unit up along the y-axis. And since we are looking at from x equal -1 to x equal 2, I want to give myself some room for this. So I'm going to say that -1 is here, and 1 and 2. And then plugging just those x values that I have there into my function, I can at least get some values to see the graph. So at -1, I would have 1 plus -1 squared, and that's going to be 2. If I plug in 0, I get 1. And if I plug in 1, I get 2 again, and then 2, I'll get 5. So there's my parabola. So it says that we want to use 3 rectangles. We could probably already see here how those 3 rectangles are going to come about, but I want to use what we just learned to see some details. So first of all, we're going to notice that A is equal to -1 and B is equal to 2. So then if we want to find delta x, we were told it should be b minus a divided by n. So that would be 2 minus -1, and then divided by n is the number of rectangles, so n is equal to 3. This gives us 2 minus -1 is the same thing as 2 plus 1, which is 3, divided by 3, and that's 1. Which should make sense. It looks like we already have 3 sections here. Okay, so this is just matching up our intuition with what we just described above in that general description. So delta x is 1. Right? And then since we want to use right endpoints in part A, I need the locations of those right endpoints. So as also described up above, we were told that x sub 1 should be start at A and then add delta x. So A plus delta x. A, again, we were given as -1. Delta x we were given as 1 after we calculated that. So it means our first right endpoint should be 0, which we can see that's definitely true. The first interval goes from -1 to 0. The right endpoint is 0. And then x sub 2 would be a plus 2 times delta x. Again, that means start at -1 and then add 2 times 1. So -1 plus 2 is 1. Again, we can see that that makes sense. 1 is the next right endpoint. And then x sub 3 would be a plus 3 times delta x, which is -1 plus 3 times 1, which will be 2. So for the right endpoints, I'm getting those heights. And you can see that right endpoints don't always guarantee an over-approximation. Like I get an over-approximation when using 2. I get an over-approximation when using 1. But when using 0, I get an under-approximation. So it doesn't matter. We can still use right endpoints. We're just getting some rectangles above the curve and one rectangle below. So then the approximate area, we can say r sub n, again going along with the sum that we talked about for r sub n. That would be delta x times f of x1 plus delta x times f of x2. And then we don't need the dot, dot, dot because I only have 3 rectangles here. So the last one is f of x sub n, but that's just f of x sub 3. So then delta x we said is 1. And then we can plug in each of those x values into our function. So this will be f of 0 plus delta x, which is 1 times f of x. Sorry, f of 1. And then plus delta x, which again is 1, times f of x3, which is 2. So then f of 0, we've already said, is 1. 1 times 1 is 1. F of 1, we already said was 2. 1 times 2 is 2. And then f of 2, we already said was 5. So then 1 times 5 is 5. And this gives us 8. So that's our approximate area just using 3 rectangles. So now let's see how this would differ with part B using midpoints. So what this means is our delta x is still going to be 1, but we need to figure out the midpoints, which means go back to your intervals that you have here and just find the midpoints in each of those intervals. So don't think too hard about this. Midpoint means just halfway. So between -1 and 0, the number that's halfway is -1/2. Between 0 and 1, the number that's halfway is +1/2. And then between 1 and 2, the number that's halfway would be 3/2. So if you think about how this is going to work, you're essentially using each of those midpoints to get a height out of your rectangle. So you would have, for -1/2, this height. For +1/2, you'd have a similar height. And then for 3/2, you would have a similar height. And again, you can think that there's going to be some over or under approximation. And you could think, okay, from -1/2, if I make a rectangle that goes to the right, it would be like this. For +1/2, I'd have another one like that. And for 3/2, I'd have another one. And so we're, again, just using these rectangles to get some sort of a guide to how our area is working. So, using midpoints, we've got delta x is equal to 1 still. We've got x sub 1, and sometimes the notation for this is x sub 1 bar, where we think of midpoint as being an average, so that's the bar notation. We said was -1/2. X bar sub 2 is +1/2, and x bar sub 3 is 3/2. So then the area, we're not going to use r sub n, we're going to use m for midpoints, and n in this case again is still 3. So I would have delta x times f of x bar sub 1 plus delta x times f of x bar sub 2 plus delta x times f of x bar sub 3. And again, delta x is still 1 unit. And then I need f of -1/2 plus 1 again for delta x times f of +1/2 plus delta x, which is 1 again, times f of 3/2. So then again, using our function, 1 plus x squared, -1/2 squared is 1/4, 1 plus 1/4 is 5/4. You would get the same output for +1/2, so we have another 5/4. And then for 3/2, 3/2 squared is 9/4, plus 1 would be 13/4. So this gives us 23/4, which would be 5.75. So you can see we get a different area than what we had from right endpoints. And it is a smaller area, which should make sense because it looks like our rectangles are below for 2 of them, and then not too far above for just 1 of them. So now to finish this lesson, let's look at the application to what's called the distance problem. So we're going to see how this applies to the relationship we've noticed many times before, the relationship between distance and velocity. So let's suppose someone is wondering how far they travel in a short amount of time when the velocity is changing throughout that time. They record the following information from their speedometer while they're driving. So here we have a table with 2 rows. First row is time, second row is velocity. So in the first row we have time notations of 0 seconds, 5 seconds, 10 seconds, etc. up to 30 seconds. And then for the velocity, we have 17 miles per hour when this person starts recording the information at 0 seconds. Then 21 miles per hour at 5 seconds, 24 miles per hour at 10 seconds, etc. So different values of velocity at different points in time. We've seen many times before that distance is equal to rate times time. To get an approximate distance traveled, this person can use the velocity for each interval of time. So, for example, from the interval from 0 to 5 seconds, this person could use the velocity that they started with, 17 miles per hour, or they could use 21 miles per hour. That's getting to the idea of left endpoints and right endpoints. So, we've got left endpoints. We've got a width of a time interval. This is reminding us of what we were just looking at. So to find an approximate distance traveled, let's use left endpoints. So here we can think that the time interval, that would be delta t if we wanted to. That's just 5 seconds. And then the endpoints that we want to think of, we're thinking that we have from 0 to 30 seconds. We're dividing that into 5-second intervals, so there should be 6 numbers that we use for endpoints. So if we use left endpoints, that would be 17. We're going to call that x0 like we had done before, but if we want to think of time instead of x, we can use t. And then the next left endpoint would be the next velocity, etc. And we don't go all the way to the end because with left endpoints we stop one before the end. So then for the endpoints, we have t sub 0, which is 0, t sub 1, which is 5, t sub 2, which is 10, t sub 3, which is 15, t sub 4, which is 20, and t sub 5, which is 25. So then we also need function values at our endpoints. And there's no function here to plug anything into. We just have outputs that were recorded for the velocity. So the velocity at t sub 0, that's 17. The velocity at t sub 1, that was 21. The velocity at t sub 2, that was 24. The velocity at t sub 3, that was 29. The velocity at t sub 4, that is 32. And the velocity at t sub 5, that's 31. So then we remember from our previous examples, we take our time interval, delta t, and we're going to multiply it by our function values. But something that we want to keep in mind is that our function values are in miles per hour. And all of those are in miles per hour. And if I'm going to do distance equals rate times time, I need time and rate to be using the same measurement of time. So instead of 5 seconds, we want to convert 5 seconds into a number of hours. So if there's 60 seconds in a minute, then 5 seconds would be 0.083 repeating minutes, where I just took 5 and divided by 60. And if I divide by 60 again, this gives me 0.00138 repeating hours. I'm just going to use approximately 0.00139. So then to get my distance, it would be my time interval times all of those function values added together, which equals 0.00139 times, and then I'm just going to add those numbers up. So 17 plus 21 plus 24 plus 29 plus 32 plus 31, 154. So that's giving me my total in miles per hour. Now I'm going to multiply by the number of hours, 0.00139, and that gives me approximately 0.214 miles. So a fifth of a mile, which when you think about the total time interval from 0 to 30 seconds, that's how far this person has traveled in just 30 seconds, a fifth of a mile. Doesn't seem too unrealistic. So again, this is just an approximation of that, but this shows you that we can use the same process we just developed to solve this problem.